Hello, we are continuing with the series on atomic and molecular spectra, and in this video, we are going to deal with the Sommerfield's Sommerfield's extension of Bohr's model. Now, the in the previous video, we had discussed about the Bohr's correspondence principle, and we had obtained a few results out of it. But now we'll be dealing with the Sommerfield's extension of the Bohr's model. And well, to start off, we have that the Bohr's model of hydrogen atom, the electron could move only in circular orbits. This restriction was entirely arbitrary. Moreover, in spite of the striking numerical agreements, the Bohr's model could not explain the fine structure of the hydrogen spectral lines. The fine structure is the splitting off of the several lines into several close, distinct components when observed under equipments with high resolution. This means that each Bohr's energy level in hydrogen atom actually consists of several components which are close together in energy. So Sommerfeld in the year 1916, Bohr's model was in 1914. So Sommerfeld, in an attempt to explain the fine structure, that is the splitting up of the spectral lines, what he assumed as an extension to the Bohr's model, that the orbits that were considered to be circular by Bohr, he considered them to be moving in elliptic orbits. So this model deals with the elliptic orbits of taken up by the electron to move about the nucleus, and thus we have this model that the extended model of the Bohr by Bohr taken up by Sommerfeld. So let's get into it. So here we have the illustration of the elliptic orbit taken up by the electron to move about the nucleus. We have the electron of mass m at a radial distance r from the nucleus, and at any given instant of time it is making an angle theta, oriented at an angle theta with respect to the horizontal line that we have indicated over there, which is the major axis that we consider of the elliptic orbit. And the nucleus has a charge of plus Ze, Z being the atomic number in this case, so the number of protons that are present within that nucleus. This is the semi-minor axis, which is indicated by B, and we have the semi-major axis indicated by A, and then we have the velocity at that instant to be indicated for the electron to be indicated tangentially with respect to that orbit that we have. So this is that tangential line that we have considered, which gives us the velocity at that given instant of time. And we can have two components of that velocity for the counterclock movement. In this respect, we have the rectangular components like this, one of which is normal to that circular or elliptical path that we have, that is r theta dot, which is omega in this case, and then we have the radial component of it, which is r dot, which is acting towards the nucleus. So these are the parameters involved, and so if we have PR and P theta to be the momenta, so PR and P theta are the radial and angular momenta. So this is the radial and this is the angular momenta that are involved, then from the Wilson-Sommerfeld quantization rule, this is in the third video of this series that I discussed. So from Wilson-Sommerfeld quantization rule, what we get, I'm writing this in short, so we get PR dr, which is the complete integral of the momentum with respect to its corresponding radial component, is equal to the radial parameter, the integer involved, multiplied with the Planck's constant h. And similarly for p theta as well, we'll be having it from 0 to 2 pi p theta d theta is equal to, it's not nr anymore, it's some other uh, parameter, let us take it as k, again an integer term, and h, that is the Planck's constant, where nr is the radial quantum number. So this is the radial quantum number, whereas k is the azimuthal quantum number. So the radial and the azimuthal quantum numbers as obtained, as given by the Wilson-Sommerfeld quantization rule, we have just we'll be using that. Now the second integral is pretty easy because according to classical mechanics, the angular momentum, that is p theta of any isolated system is a constant, so that can go out of the bracket. So for the second integral that we have over here, p theta goes out of the bracket, and you have 0 to 2 pi for that d theta, which will give you 2 pi eventually. So that gives me p theta to be equal to kh divided by 2 pi. Now this is in absolute agreement with this kind of restriction is an absolute agreement with that obtained for Bohr's model in case of circular orbit. Now in order to obtain the first integral, we know PR is equal to mr dot, and p theta is obviously equal to mr squared theta dot. So as I had indicated that r dot and theta dot, they are r theta dot are the two components of the velocity that we get over there. Now the polar equation of the ellipse, the polar equation of the ellipse, what does it give us? The polar equation of ellipse gives us 1 by r to be equal to 1 by a, where a is obviously the semi-major axis, multiplied with 1 minus the eccentricity. Now we usually denote it by small e, but here, because small e has been indicated as that for electron, we'll be using somewhat this kind of e. So be careful about that, about the notation that I'm using over here. 1 minus e cos theta divided by 1 minus e squared. And as you know, for an ellipse, 1 minus e squared under root is simply the ratio of the semi-minor to the semi-major axis. Let me just indicate it over here. 1 minus e squared under root is the ratio of the semi-minor to the semi-major axis. So this is just for a reference what we are dealing with. Now we can take the logarithmic differentiation of r with respect to theta. If we are to take that differentiation, then what we get, 1 by r squared, this becomes minus 1 by r squared for differentiating with respect to theta. We have dr by d theta, and on the right hand side we just end up with the term over here is the same, but the only problem that we face is on the numerator, where minus e cos theta is going to be e sine theta cosine theta. When uh, taken derivative with respect to theta will give me minus sine theta, so that minus term will cancel out. The first term, that is 1, is a constant, so that does not count, that goes to 0, and the denominator as a multiplicative factor, that remains as such. So what we end up with is that 1 by r, because 1 by r that I have over here, let me name this as a and this equation as b. If I divide the equation b by the negative of equation a, so what I'm doing is I'm dividing b divided by the negative of equation a. Now these are equations, so I put them in bracket because you may confuse it with the semi-major and minor axis. So this is the equation b divided by the negative of equation a. What do we end up with? We get 1 by r, and dr by d theta remains as such. There is no division in that case. And over to the right hand side, what we get is the 1 by a's cancel out, and e sine theta remains as such, and the denominator terms, they cancel out, and because I have divided with the negative of a, so I can put a minus sign over here extra, and I have 1 minus e cos theta. It seems pretty simple. So e sine theta divided by 1 minus e cos theta in negative. And if I take if I square it further, what do I get? So I'm squaring them. So on squaring it further, what I get is 1 by r squared dr by d theta squared. I can just take the square entirely over here. On the right hand side, what I'll be doing is e squared sine squared theta divided by 1 minus e cos theta whole square. Now this is a process that we have started, and we are going to find results out of it, so stick around for the mathematics. So what do we have now? Well, we know that PR is equal to mr dot, which means it is simply equal to m dr by dt, or we can also write it as m dr by d theta divided by dt, and this is equal to m dr by d theta dot. Now PR is equal to, therefore, p theta divided by r squared dr by d theta. How does that happen? Well, m theta dot is nothing but m theta dot into r squared is p theta, since p theta is equal to mr square theta dot. So m theta dot, with the r square going down, we are leaving this with like this. So m theta dot is equal to p theta divided by r square. So these two terms, m theta dot is p by r squared, and then we have the dr by d theta. Now with that available to us, we proceed further, as we know dr is simply equal to dr divided by d theta multiplied with d theta. So PR dr is going to be p theta, and if you observe closely, we have 1 by r over here, dr by d theta whole squared multiplied with d theta. Now these two when multiplied is going to give me this, and when these two are multiplied, they are going to give me this, because dr by d theta we have them twice. So this is dr by d theta whole squared. Also the r square in the denominator, so things settle pretty well. Now we know what this term is. This term, if you remember, is simply this term that we had obtained right at the denominator there. The whole square term and all of that. So we just replace this over there. That is p theta, pr dr, that is equal to p theta multiplied with this term, that is e square sine square theta, divided by this 1 by 1 minus e cos theta whole squared multiplied with d theta. Now in order to obtain the integration of the left hand side, we just integrate the right hand side. So pr dr when integrated is going to give us the integration of the right hand side as well. For the right hand side, what we have is p theta can go out of the integral term, and this is from 0 to 2 pi, and this remains e square, obviously this is d theta, e square sine square theta d theta divided by 1 minus e cos theta whole squared, and this will be equal to, because this is what we are integrating for, so the right hand side will be nr times of h. We have just obtained the p theta form of pr, so that's for the integration part, but the right hand side is nr times of h, nr being the radial quantum number. Now this integration, I'm not going to go into the detail of it. This integration is going to be 2 pi times of 1 minus 1 by e squared under root minus 1, and the p theta remains as such, and on the right hand side we have nr times of h. So now we have some value with us, but we know p theta is equal to kh by 2 pi, so we can put that over here, and the 2 pi's will get cancelled out. What we are left with is 1 minus e squared minus 1 is equal to nr into h. So we have done away with the p theta part. Now, so what we end up with is that 1 by 1 minus e squared under root minus 1 is going to give us nr divided by k, that is the ratio of both those quantum numbers. And finally 1 minus e square, if you were to calculate it directly, the plus 1, the 1 goes to the right hand side, becomes plus 1. We have nr plus k divided by k, the reciprocal of that, k divided by nr plus k. So this, and this is obviously equal to b by a. So now we have the ratio of the semi-minor and the major axis of the ellipse, and we may put some values, that is we take nr plus k to be equal to simply n, which is the principal or total quantum number, because they are just the integer terms. They will result in another integer, another quantum number, which is the total or the principal quantum number. Now in order to exclude the pendulum of the orbits to pass through the nucleus, we do away with the case of the azimuthal being equal to 0. So the azimuthal is always not equal to 0, because in that case, if that is equal to 0, what means that the electron will pass through the nucleus, which is not possible, as we'll be seeing in case of the Heisenberg uncertainty rule in quantum mechanics. So here we are excluding this k to be equal to 0, so k is always going to be equal to 1, 2, 3, and likewise, while the case of um, nr, that is the radial term, that can be equal to 0, 1, 2, and likewise. So n is definitely not going to be 0. N is, because it is a sum of nr and k, so n will never be equal to 0. N will always be equal to 1, 2, 3, 4, and likewise. Now from this, what we get is we can just say that b by a is simply equal to k divided by n, is what we have obtained over here. And this is the quantum condition for the elliptical orbits. Quantum condition for elliptic orbits. And out of all the classical possible ellipses, the electron can move only in those orbits for which the ratio of the minor to the major axis is the ratio of two integers. So that is what we have ended up with. This quantizes the size and the shape of the allowed elliptic orbits. Now let us move over to calculate the total energy of the allowed orbit. So we are off to calculate the total energy of the electron in the allowed orbit, which is elliptical, and it follows the quantum rule that b by a, that is the ratio of the minor to the major axis, is equal to k by n. Now the total energy is obviously the sum of the kinetic energy term. Remember, this is k in capital or big letters, as opposed to the k in case of the azimuthal quantum number, so don't confuse with that. And we have the potential energy term u. Now this kinetic energy is obviously equal to half mv squared. V, remember, can be written as the r dot, that is the radius dot, the first derivative of the radial term, and this is r squared theta dot squared for the potential, for the radial in terms of the angular kinetic energy term. And finally, those are obviously both those components, the radial and the tangential part. And then we have the potential energy term, which is simply obtained by the electrostatic potential energy. That's all we have, and we'll just be putting them together in terms of the momentum that we have calculated, that is pr squared plus p theta squared by r squared, and minus 1 by 4 pi epsilon naught ze squared divided by r. Now this is somewhat the equation that we have ended up till now by using the previous equations that we have. We'll be further using the condition where we are converting the PR entirely to P theta, so that we are ending up with P theta squared divided by 2m, and the r square even is taken as common, and here we have the, as because PR, we had obtained the value of PR, isn't it? PR is equal to P theta divided by r squared dr by d theta. So PR is equal to P theta squared, that has been taken outside, divided by r squared, that has also been taken care of, and finally we have dr by d theta over here, and that is completely squared, and what we can do is we can add another 1 by r, which will be taken out from this term, and we are left with just 1 over here, minus 1 by 4 pi epsilon naught ZE squared divided by R. This is simply a mathematical manipulation that I did. I hope you get it. In case you don't, I'll try and do it once more for you on the left hand side. PR is equal to P theta divided by R squared dr by d theta, and the square of it, that is PR squared, because we have the PR square in those brackets. So PR square is going to give us P theta squared. We can write this R squared 2 times instead of R to the power 4, and finally dr by d theta whole square. So what we get is that P theta squared divided by R squared, which has been taken out of the bracket, as you can see, and one of those R squared has been included, 1 by R dr by d theta whole squared. Well, that's because you know that what we are going to get into, because if you have been following, then the calculation that I've made, this makes a very important part of it. So that's where we have reached as of now. Then over to the next step. What we get is that 1 by R squared, 1 by R dr by d theta squared is equal to the E term that was on the left. We simply cross multiply a few terms. What we end up with is 2me divided by P theta squared, and then we have minus 1 for that plus 1 that was there inside the bracket over here, and then we have the other term, that is the potential energy term, over to the other side becomes plus m times of ZE squared R divided by 2 pi epsilon naught P theta squared. Now we have a thing where we have 1 minus E cos theta, if you remember, is equal to A by R times of 1 minus E squared. Well, we had obtained this on the previous occasion from where? Well, from the polar equation of the ellipse. Let me get back to that. From the polar equation of the ellipse, that is over here, right there, the equation A that we have, this one. So in that equation, A by R is going to give us 1 minus E cos theta divided by 1 minus E squared. So 1 minus E squared gets multiplied to A by R, and we have 1 minus E cos theta. That is what we have done over here. So this is from equation A. Let me just clarify that. So this is from equation A. Now remember, this formula will be doing a few steps associated with that. From this we can also obtain E square sine square theta, and that will be equal to, if you calculate it and calculate it well, you will find it to be equal to E squared minus 1 minus A square 1 minus E square whole squared divided by R square plus 2A 1 minus E square divided by R. I insist that you try this step so that you will understand how important it is. So E square sine square theta is this much. Now if I divide this equation C and I take this as equation D, so now I divide equation D, divide it with that equation C, what do I end up with? On the left hand side I have E square sine square theta divided by 1 minus e cos theta, but hang on a second, I'll take 1 minus e cos theta whole squared. So I'll be squaring the equation C, and that will be equal to, what I'll get over here is minus r square divided by a square 1 minus e square minus 1 plus 2r 1 minus e squared. Now I have confirmed with my rough work that I have done for this, so I'm writing it straight away so that I don't waste your as well as my time. But what about this thing that I've done, and why did I do it? Well, if you remember, this exact thing is nothing but equal to this. So what I get is, by comparing these two, I end up with the case that all the terms must be equal. So the minus ones are okay, they have been taken care of. What about the other two terms? Well, in the other two terms we therefore have 2me divided by p theta squared, that is the first term of this equation. 2me by p theta squared is going to be equal to minus 1 by a squared 1 minus e squared. And what about the third term? Well, in the third term we have mz e squared okay, there was an r square over here, so I had left that. So the first term is taken care of. The r square has changed or has been taken common. And what about the third term, that is mz e square, the component of r, that is, divided by 2 pi epsilon naught p theta squared is equal to 2a divided by 2 divided by a times of 1 minus e squared. Now we are taking this as equation E and equation F. So now if I divide the equation E by the square of the equation F, then what I have is simply, on the left hand side I have 8 pi squared epsilon naught squared p theta squared divided by, obviously we have the e term over here, and that divided by the mz square e to the power 4, and this will be equal to, onto the right hand side we have minus b squared divided by 4a squared. Now with this thing we have b square by a square term. So now let's obtain the energy that we were supposed to calculate. So we have E to be equal to minus m z square e to the power 4. Now you can see we are getting close to that Bohr's answer, Bohr's result, 32 pi square epsilon naught squared, and this is p theta squared, and then on the top we have b square by a square. Now this b square by a square is simply going to give us k by n squared, and p theta is simply kh by 2 pi. So we put all of that. For p theta we put kh by 2 pi, and for its square we put it as square, and here we put k by n for b by a and square of it. So the k squares get cancelled out, and the 2 pi square cancels out with one of the the pi square and the pi square for 32, that also cancels out, and the 2 square 4 gives us 8 when cancelled with 32. So finally we have the expression to be somewhat almost completely similar to m z square e to the power 4 divided by 8 epsilon naught squared h squared, and to multiply to that we have 1 by n square. So this is completely or exactly the same as that obtained for Bohr's circular orbit. Fascinating stuff. But what have we used over here? We have used the quantization rule for the elliptic orbit that has been had been taken up by Sommerfeld, and it was quite a successful attempt to obtain this same result. And in the process he also tried to explain the splitting. Let's see how far it went in that case. Obviously he was successful in treating the elliptical part of it, as we can see as of now. Now with the energy results at hand, and the energy of the electron in the elliptic orbits, so let's just take a look at the size and shape. Before moving further, let's get into the size and shape of the Sommerfeld elliptic orbits. How and what shapes do they take up for the various energies and values that we have obtained so far? Now from that equation F that you see right there, from that equation F, well, not from the equation F, to be exact, we can choose. Okay, let's try that equation F over here. What we get is A to be equal to, let me write this in a separate ink, A to be equal to mze squared divided by 2 pi epsilon naught p theta squared, that is on the left hand side, and this 1 by e squared and the 2 gets cross multiplied, so 1 minus e squared divided by 2 gets cross multiplied. Now remember, 1 minus e squared is equal to b square by a square. So what we get in this is, I simply take it as I put the value over there, so I get mze square divided by 2 pi epsilon naught p theta squared b square by a square times of 2. 2 can get multiplied over here to give me 4 pi. Well, I'm sorry, I have 1 by a on the left hand side. So what I do is I can cross multiply the a term over here. So from the left hand side I cancel out one of the a's, and I have a to be equal to mze squared divided by 4 pi epsilon naught p theta squared b square by a. That's exactly b square. Now that is exactly what I had obtained. With that done, we can cancel out the values by putting them, and for n is equal to 1 we have the value of a to be equal to that, and we have the smallest Bohr radius or Bohr orbit for hydrogen atom, that is, we are taking z is equal to 1, we take it as a0 or a naught, and that is therefore equal to h squared epsilon naught divided by pi m z, no, not the z, but E squared. So h squared epsilon naught pi m E squared. Now with that being the smallest Bohr orbit, radius of the smallest Bohr orbit, we put the value, having known the value of b, in general we can put the value of a to be equal to n square by z a0, and also in case of b being equal to ak by n, we have the value of b to be equal to n by z k a0, because one of the n's get cancelled out. So these are the values of a and b in general that we have obtained. And let's see what we can predict, the theoretical prediction. Now the theory predicts that n is equal to k plus nr, and n can take possibly the k can take n possible values, and this means that for a given n, there are n orbits. For a given n, there are n orbits of different eccentricities, of different eccentricities because we have different uh, as per the condition b by a to be equal to k by n. So from that we have those values which can be occupied by the electron. Now for z is equal to 1, we have n is equal to 1. Considering that, we can take k to be equal to 1. Remember, k can take n number of values. Now if we put this k is equal to 1, n is equal to 1 in this equation, the eccentricity reduces to 1. So we have a to be equal to a0, and also if we check for b, that is also equal to a0. That means it is completely a circle, so it takes up a complete circular path. That's more or less the kind of circle that I have drawn. Let me draw it clearly for you. So with that circular path, we have the radius to be equal to a0, which is the circular Bohr's orbit for hydrogen atom. Now for n is equal to 2, we have k to be taking k is equal to 1 and k is equal to 2 values, and for that correspondingly we have the value of a and b to be 4a0 and 4a0 for a and b, and 4a0 and 2a0 for a and b in case of k is equal to 1. And likewise we have two eccentricities over here, that is for b is equal to 2a0, and we have this to be b equal to a, which is equal to 4a0, which is this case, and this is the other one. So this is one more step that we get into while considering the eccentricities and the various values that are taken up for n, for different values of n. Likewise for n is equal to 3, we have k to be taking 1, 2 and 3 values, and for that we have the values of a and b. For k is equal to 3 as 9a0 and 9a0 respectively, giving a circular orbit. Then for k is equal to 2, we have a to be equal to 9a0 and b is equal to 6a0, which is giving us an elliptical orbit, and a further squeezed up or with a greater eccentricity that we see over there, the third kind, where we have A is equal to 9a0 and B is equal to 3a0 for K is equal to 1, and this is for N is equal to 3. So we see that the corresponding to each value of the principal quantum number, there are n different allowed orbits. Out of these, there is the circular, which is described by the Bohr's theory. The others are elliptical, we're all having the semi-major axis and as the radius of the circular orbit, but different semi-minor axis. The orbit having the lowest k is the most elliptic for sure. But despite the very different paths followed by the electron moving in different possible orbits for a given n, the total energy of the electron remains the same. This means that Sommerfeld's introduction of elliptical orbits adds no new energy level, and hence it fails to explain the fine structure. The several orbits characterized by a common value of energy are said to be degenerate. So we are having a degeneracy case that is arising over here. To designate an orbit of given n and k value, we follow the case of the S, P, D, F, G letters, which correspond to k is equal to 1, 2, 3, 4, and 5 respectively. For example, for n is equal to 3, take the example n is equal to 3, k is equal to 1, it is written as 3s, where k is equal to 1 corresponds to the S shell. And again, for n is equal to 3, k is equal to 2, we have it as 3p. And likewise, it is seen that the s electron orbit with the lowest k is most elliptical in a family of orbits having same major axis, that is the same value of n. So with this we end with today's with this video, and we'll be continuing with the corrections that were taken up by Sommerfeld, especially the relativistic corrections that were taken up for obtaining the splitting conditions of these shells. But will that resolve the things that are um that were not available to us? Will that resolve all those problems? Is still a question to be answered, but that will be dealt with in the next video. Till next time, thank you for watching.